Oh, howdy, students. This is going to be Unit 14. We're going to move into acids and bases, which are chemical compounds that fall into their own little subcategory. And this is going to be part 1. So in this video, we're going to cover properties of acids and bases, and then we're going to look at what we call the pH scale. And there's a few calculations that are associated with that. You will need a calculator as you complete notes for this video, so make sure you have a calculator nearby. So the first thing we're going to talk about are acids. Acids tend to taste sour or tart, like vinegar and lemons. They are aqueous solutions. When they're in aqueous solutions, they form electrolytes. So in the electrolyte demo, it would light up the light bulb because ions are formed when the compounds are dissolved in water. They cause these indicators, which we'll learn about in our next video, to change colors. And specifically, a lot of times we see red and orange and yellow associated with acids. Many metals react with acids to produce hydrogen gas, and that's because most acids have hydrogen in their formula. They react with hydroxides, which hydroxides are OH minus, if you remember from the ion chart, to form a salt and water. And in chemistry, we can have lots of different salts. Usually a salt in chemistry is a group 1 metal with a group 7 halogen, generally. Most formulas begin with H, which is how we form that hydrogen gas when we mix it with metals. So look for an H, and generally the H is going to be on the left side of the formula. The pH value, which we'll discuss later in this video, is less than 7. The pOH, which we will also discuss later in this video, is greater than 7. So these are values that classify a compound as an acid. And then we're going to learn about the concentrations of hydronium, which is H3O plus hydronium, which would be greater than 1 times 10 to the negative 7th, or hydroxide, concentration, which would be less than 1 times 10 to the negative 7. And again, we'll talk about this later in the video. We're going to produce H3O plus or H plus in watered solutions. So when we talked about electrolytes above, the H plus or the H3O plus, the hydronium, that is going to be responsible for helping us light up our light bulb when we conduct electricity. Now, bases. Some would say they're opposite from acids. Generally, acids and bases react together in what we call neutralization, which is what we cover in Unit 15. Bases produce OH in water solutions rather than H plus like acids did. So we have this hydroxide being produced. They have a bitter taste instead of a sour taste, like soap, unsweetened chocolate. Those tend to be bitter. They feel slippery to the touch. So if you've ever felt soap or even some sort of household cleaner, generally those are kind of slippery. They react with acids to form salt and water. So this is the same as an acid. So some of the properties are similar. They cause indicators to change colors. Okay, once again, that's the same as an acid. But generally you see blues and purples and dark greens with bases. They contain hydroxide in their formula. So look for OH in the formula. Bases are electrolytes in aqueous solution. So again, this is the same. That would also light up our light bulb. The pH values are going to be the opposite from acids. So pH value greater than 7 and a pOH value less than 7. The hydronium, or what we're also going to refer to as the H plus concentration, is less than 1 times 10 to the negative 7th, or the hydroxide concentration is greater than 1 times 10 to the negative 7. So here's a question. A substance has a formula of HX and has a pH of 4. Is it an acid or a base? So two things. If this is my formula and I see that it starts with a hydrogen, that indicates an acid. And if it's a pH value less than 7, then we have an acid. So on both accounts, this is an acid. Label the following: A if they're acids, or B if they're bases. First one, I see hydrogen as a part of the formula. That's an acid. We call that sulfuric acid. Vinegar, well, in our properties, vinegar was something that tasted sour or tart. And if I actually write out the formula, HC2H3O2, I'll see that I have a hydrogen there. So on two accounts, we have acid. Soap, mentioned above, slippery. That is going to be a base. That would definitely taste bitter. Strontium hydroxide, we have this OH here, which is indicative of a base. pH value less than 7, that would be an acid. And then a pH value equal to 11, well, that's a pH value that's greater than 7, which means base. Common uses of acids: HNO3, which we call nitric acid. You may want to write that in there. We'll see it later. Nitric acid or hydrochloric are used for etching metals. So if you let acid sit on a metal, sometimes it'll scratch away at the surface, probably producing hydrogen gas when that happens. And then hydrofluoric acid is used for etching glass, so it can actually eat at glass surfaces. So the hydroxide ion, which again we look at when we're talking about bases, are formed when a water molecule loses a hydrogen. So if we start out as H2O, which we can also say HOH, same thing. If we lose an H plus, what we have left over is an OH minus. We call this the ionization of water. So when that happens, we can also form a hydronium ion, which is formed when a water molecule gains an H. So in the picture below, you'll see we have two water molecules. One of the hydrogens here is going to remove itself and attach it to another water molecule. And that's how we get hydronium and OH minus. So the formula for the production of hydronium is shown below here. H2O plus H plus yields H3O plus, and it's an ion. It is a positively charged ion. So some people consider this a polyatomic ion. We had one other positive polyatomic ion, which was NH4 plus, and here's another one we can add to our list. So sometimes in this unit, we will say H plus or H3O plus, and generally in this unit, we are talking about the same thing because what we're measuring is the hydrogen that is floating around in solution. So the pH concept, we use what we call the pH scale to measure out how many hydrogen ions are in a solution. A lot of times we call this the power of hydrogen. We can calculate the pH of a solution by using this equation. And I'm going to star this because this equation is very important for calculating pH. What we'll take is the negative log, which I'll show you on the calculator in just a second, or the negative log of H plus. So again, H3O plus and H plus are interchangeable. Same thing in this unit. So this uses a logarithm. A logarithm is the exponent to which 10, so a lot of times logarithms are base 10, must be raised to get the specific number that we're talking about. So let me show you on a calculator here. When I have my calculator on, if I want to calculate, and we'll do this on the next few slides, I just want to point out that the log button is down here, but it's a negative log. So when I'm solving, I will hit the negative button down here first, and then log, and then I'll punch in whatever my value is, and I'll close parentheses. So if H3O plus concentration, we see the brackets there, is 1 times 10 to the negative fourth, then what we would do is take the pH equals negative log of 1 times 10 to the negative fourth, and we'll get a pH of 4. So let me show you that. I would do the negative log of 1.0 times 10 to the negative fourth, which I can still use my shortcut, second comma, which gives me E, which is times 10 to the negative fourth. And when I hit enter, you'll see that my value is 4. Now let me show you, I can type it out fully and say negative log, and then I can do 1.0 times 10 to the power of negative 4, close parentheses, and we still get the same value of 4. So we can have a range. The range of the pH scale is from 0 to 14. You'll see that down here. Acids can go down as low as 0. Bases can go as high as 14. And then right in the middle, we have our neutral value of 7. Lots of different materials and substances have different pH values. You'll see acids on the left and bases on the right. And then in the middle, we have neutral substances like blood, seawater, baking soda, and milk is close to being neutral as well. So what is the formula for pH? Let's summarize. pH is going to be equivalent to the negative log of the H plus, or what we call the H3O plus concentration. So if the pH is known, we can also calculate the concentration by using what we call an anti-log. So the formula is H3O plus concentration equals the anti-log of the negative pH. So make sure we are aware that there is a negative value there in that formula. Okay, so let's practice. Make sure you have a calculator here so that you can get the practice that you need. To find the H3O plus concentration, I will need to use my formula. pH equals the negative log of H3O plus. So let's do that. And then the concentration of H3O plus is equivalent to the anti-log to the negative pH. So in this case, we're going to take the anti-log, which is, we're going to hit the second button, and we're going to hit log. So the anti-log is just 10 raised to the power. So anti-log is 10 raised to the power. So in this one, I'm going to do 10 raised to the power of negative 3.44, close parentheses, and there's my answer. And then I'll round to, they rounded to 2 sig figs here. I would probably have taken 3. So let me grab that calculator again. I would probably change that to 3.63 times 10 to the negative fourth. Okay, let's keep moving forward then. We're going to do the negative log. So second log to the negative 11.92, close parentheses, and here's my value. I'm going to round to 4 sig figs here, 1.202 times 10 to the negative 12th, excuse me, not the 21st. And then the last one, we'll do an anti-log, second log to the negative 8.334. We'll round to 4 as well, 4.634 times 10 to the negative 9th. So before we move on, let's go ahead and check our answers there to that one. Yeah, so I would have rounded to the sig figs that were given. And then let's do the opposite here. We have the concentrations on this side. We need to find pH. So for this one, we're going to do the negative log of these pH values. So 1.39, I'm going to use the shortcut, second comma, -3. And I'm going to use 3 sig figs here, so 2.86. Next one, negative log of 8.23. E, second comma, E, -6. And I'm going to round to 3 significant digits, 5.08. And then last but not least, negative log of 9.95, second comma, -2, close parentheses, and that gives me 1.00 for my pH. Now, before I move on, I can also now label these as acidic or basic. So I'm looking at the pH values. Acids will be less than 7. So this is an acid, acid here, acid here, acid here. Bases will be greater than 7. So this is a base, base, and we can label according to the values. So what is the pH if the H3O plus concentration is 1 times 10 to the -5th? Well, there's actually a shortcut. I'm going to show you that right here. If the coefficient is 1 or 1.0, we can actually just look at the exponent, take away the negative, and that is the pH value. So there is a shortcut here. But it does not work if the coefficient is not 1. So I think that's what they're going to show here. Now, same thing here. We have 1 as a coefficient. So the pH is 13, which would give us a basic value. Now, on this one, we have to actually calculate it because we have 3. So I would have to do the negative log of 3, second comma, to the -7. And that would be a pH value of 6.5. If you round to 1 digit, it would be 7. So in this case, it looks like we have a neutral value. So they labeled acidic, but according to the sig figs, I would label that as neutral. And then here's just a quick summary of the pH values. So how do we know if a substance is acidic or basic from the pH? And so I'm going to point you back to this slide right here for the answer. This is what tells us. The pH is not actually the only part of the pH scale. We also have something called pOH, which is a measurement of hydroxide ion concentration in a solution. It can be calculated using the following. pOH is equivalent to the negative log of OH minus. So it's the same equation, but instead of pH, we're using pOH. If the pOH is known, you can use the following to find the OH concentration. Again, you'll find it's the same equation, but we're using pOH. So what we need to know is how to go from pOH to H+. So let's go through these. We have the pOH values. So we're going to find the concentration by using the anti-log. So the anti-log, second log to the negative 11.9. 1.26 times 10 to the -12. You can also do it on your own. 10 raised to the power of -3.44 is 3.63 times 10 to the -4th. And then, once again, to the power of -6.57. We always make it negative. 2.69 times 10 to the negative 7th. Let's scoot on over. Now I can use the negative log of 9.85 to the power of negative 11. And that gives me 10 point. And here, I'm looking for 3 sig figs, so 10.0. And then negative log of 6.523. E negative 8. Which gives me 7.186. And then one more time, negative log of 8.7. Notice how I don't turn this negative. Second comma to the negative 3. And 2.1 for our pH. Okay, just like pH and pOH are related to one another, just like the concentration of H3O plus and OH minus are related to one another. So we're going to connect pH, pOH, concentration of H plus, and concentration of OH minus. So if we want to connect the two, here's another equation here. pH plus pOH equals 14. They add up to 14. If the OH concentration or the H plus concentration is known, it can be used to find the missing component using this equation, which we call the dissociation constant, 1 times 10 to the negative 14 equals H3O plus times, and this is a times symbol in here, where this was a plus, in order to find these two. So let's fill out this chart together. I'll work through it. So first thing, on the first row, I have the pH of 9.455. So to find the pOH, I'm going to do 14 minus 9.455 because they add up together. Missed that one. 14 minus 9.455. There's my answer. 4.545. I'm going to keep going down the row here. pOH to pH, I'm going to do the same thing. 14 minus 7.11. Which will give me 6.89. 14 minus 0.482 gives me 13.518. Now, if I go over here, I can use the second equation to calculate the OH concentration and the H plus concentration. So I'm going to take parentheses. I usually like to add parentheses here. I'm going to do 1.0 E negative 14, which comes from my equation here. And I'm going to be dividing by 1.02 E negative 4. So my OH concentration is 9.80 times 10 to the negative 11th. I'm going to do the same thing. 1.0 E negative 14 divided by 4.93 E negative 9. And I'm going to get 2.03 times 10 to the negative 6. And last but not least, 1.0 E negative 14 divided by 9.331 E negative 8. Final answer for the H plus concentration, 1.072 times 10 to the negative 7th. Okay, now I would let you go ahead and convert these last few on your own for extra practice. So the self-ionization of water is when we take water and we bust it apart into its ions. So we have two waters, breaks apart into H3O plus and OH minus. We can also say that H2O breaks apart into H plus and OH minus if we just have a single one. This occurs to a small extent in pure water at 25 degrees Celsius. The H3O plus concentration and the OH concentration are equal to 1 times 10 to the negative 7th, which is considered neutral when they're the same. In any neutral solution, we have these all equal to each other. The ion product constant for this equation, so the K equilibrium expression that we talked about last unit, is going to be H3O plus times OH minus, because this is a liquid up here, and we don't include liquids in our KEQ expression. The equilibrium constant is 1 times 10 to the negative 14th. That's where we get that number from. And to summarize, this magical pH box of power shows you all of the different equations and when to use them. So when in doubt, when you get stuck, reference this awesome pH box of power and it will set you free.